Okay. So let's say you're given a vector field like this. And today we're going to ask for the following. First question is, check that F is conservative. And second part is, find f(x, y) such that f is gradient of f and f 0, 0 is 0. So in other words, you're trying to find an antiderivative of this vector field. Right? We talked about how a vector field being conservative means that it's a gradient vector field of some function, multivariate function f. And the second part is asking for us to find out what that function f is. Okay? And just like how you find the antiderivative in the usual calculus 2 context, you always get the integral constant plus c, right, when you integrate, right? And you need this extra condition in order to figure out the exact value of c, right? So sometimes I might provide you this, or sometimes I may not. Then you just put plus c in general without really figuring out what that is. So this one you may or may not be given. It's not too important. What's important is first how to check that it's conservative, and B, how to find out the function, multivariable function, whose gradient is on the vector field then. Okay? All right, so let's try to solve this. All right. What does it mean to be conservative? Conservative means that the curl of f is 0. Now the trouble with the usual textbook definition of the curl is that they only define it for 3-dimensional ones. But I like to call this other one also as curl. So our 2-dimensional version of curl, 2D version of curl, is the following. You do partial with respect to x, partial with respect to y, and then you put u, v, where your f is really u to v. Okay, so let's compute that. So if that determinant turns out to be 0, then we know that it's conservative. If this determinant is not equal to 0, then it's not conservative, and in that case, there's no way that you can find the function whose gradient will be equal to the vector field f. Okay, so that was the theory that I tried to explain in a rather roundabout way, talking about all this line integrals and stuff. But that's what it boils down to. So from now on, every time you're being asked to check that a given vector field is conservative, so simply compute this quantity. If it's equal to 0, then you've proved it. Okay? All right. So let's try that. If I have differentiation with respect to x and differentiation with respect to y, and I put over here 3xy plus 5 cosine x and 4y squared plus 3 over 2x squared. Let's compute this. Now, how do you compute this determinant? It's like this, right? So this hits this, minus this hits this. So you have to do partial with respect to x. This is not 2, it's partial derivative. Partial derivative of 4y squared plus 3 over 2x squared minus partial derivative with respect to y of 3xy plus 5 cosine x. And then partial derivative treats the other variable as a constant. So if you differentiate 4y squared by x, you get 0. And if you differentiate this by x, you get 2 comes down and you get plus. Come on, help me out here. What is this? What's the derivative of this with respect to x?
3x.
3x, thank you. All right, and then if you differentiate this by y, you get 3x. If you differentiate this by y, you get 0. Therefore, you end up with 3x minus 3x, which is equal to 0. Now, I purposely wrote down the curl this way because this is the way that we're going to be using the curl when we go to the Green's theorem soon. Okay, but maybe because this is not what I wrote down last time, you might be a little confused what this has anything to do with the other definition of conservative that I talked about. So let me write down what this means. This means round x hitting v, so it's like v differentiated by x. And this is round y hitting u, so that's u differentiated by y, and you're subtracting it, right? And then think about what it means for this to be 0. That means if this is equal to 0, that means if I take this and differentiate by x, if I take this and differentiate by y, and they're equal. That's actually exactly the definition that I was using for being a conservative vector field. Right? Saying something is a gradient vector field means because the second partial is commute, this one, which is f differentiated by x, if I differentiate by y, it will be fxy. And this one, if I differentiate by x, then since this is already f differentiated by y, it will be fyx. So just simply this fxy equals to fyx. The requirement that this should hold is equivalent to saying that this should be equal to 0. Okay, so that's how everything is related, right? But you don't have to write all that. You just simply, when you're being asked to check that something's conservative, just simply compute this, and it's equal to 0. Then it means it's conservative. And if it's conservative, that means there must be some function whose derivative is equal to this one. Okay. All right, so let's continue on. So that's just part A. We've done part A. Now part B. What is gradient of f? Gradient of f is f differentiated by x, f differentiated by y. And I'm trying to set this equal to 3xy plus 5 cosine x and 4y squared plus 3 over 2x squared. I'm trying to find a single function whose partial with respect to x is this, and partial with respect to y is this. Who am I? It's basically solving a piece of puzzle. All right, first, if f partial with respect to x is 3xy plus 5 cosine x, you can differentiate both sides by x, right? And that will be my f. F would be taking this f which was differentiated by x, and you integrate by dx, then that's this should be true, right? If you take a function, differentiate by x and integrate by x, you're going to recover your function f again. And since we're claiming that this fx must be same as this one, I replace fx by this thing, I integrate, okay? So let's integrate 3xy by x. What do you get?
3x squared
3 over 2 x squared y. How about this? 5 cosine x.
5 sine, or 5
Plus 5 sine x. Right? Okay, and then you put plus c. Okay. But there's a catch. There's a difference between having integration, the honest integration, and having a partial integration. See, here, f is being differentiated while considering y as a constant, right? So if you integrate by x, this is also integrating while considering y as a constant. So this constant that you write down here could have been a function of y. Does that make sense? I mean, think about it like this. If f had this with some function of y, what will be the partial with respect to x? It's going to be this thing. Is that right? This will differentiate to this will differentiate to this, and if you differentiate this by x, you're going to get 0. Okay? So that's the big difference between your calculus 2 integration and the integration here, because this is like partial integration. The constant is rather a function of y. Okay. Now let's try to play the same game here. Now let's move on to this next one, which says f must be equal to integral of f differentiated by y dy. Okay. And that means I have to integrate 4y squared plus 3 over 2x squared by y. Y squared, if you integrate by y, that's y cubed over 3. So you get 4 over 3y cubed plus 3 over 2x squared. That entire thing is considered as constant. So if you integrate by y, you simply attach a y. And then what should I write over here? A function of what?
X.
A function of x. Let's use h for the other function. I can't. It could be different. All right. Now, if this was simply a constant, then I don't have to do the second work. I can just say, oh, so that's your function, and I just have to figure out what that constant is simply by using this condition, right? However, just as I explained, there is this unknown function of y that we have no idea of, okay? And the only way to figure out what this g of y is to use the second part. So you basically have two different views of the same function, okay? So it's like this. The structure of the function is, if you look at this, you see that this is common, right? You see those two green things that are common, right? So the function f looks like 3 over 2x squared y because both of the views says so, right? But it's like in one view I have the function of y that's hidden from us, right? And in another view I have a function of x which is hidden from us, okay? But luckily one of them shows the other one. So what's the function of y that's hidden from us? What is this mysterious gy according to this description?
4/3.
4/3 y cubed, right? So you know that it must be 4 over 3y cubed. Okay? And then what is this mysterious h of x according to this description? It must be 5 sine x, right? It's like having one person, and you need to know more about this one person. And because you can't talk to this guy, you talk to two of his friends and get two different descriptions, and you have to kind of match the different descriptions to get a single correct description of this person. Okay, and that's what's happening. So it's like this, and plus 5 sine x. Okay, and then finally you could have a plus c. And what's left to do is you should try to check that indeed the gradient of this function produces this vector field that we were given. Right? If you differentiate by x, of course constants vanish, right? And then you differentiate this by x, you get 3xy. This vanishes and this becomes 5 cosine x, so it's exactly same as the first one. If you differentiate this by y, that vanishes. All you have to do is differentiate this by y. And this goes away, and 3 comes down, and you get 4y squared, which is exactly the same as this. Okay? So you can do a quick check to find out that indeed gradient of f is equal to the vector field f. Okay? And then finally, just to check that this is true, what's f of 0? 0, according to this description, it's 3 over 2, 0 squared, 0, plus 4/3, 0 cubed, plus 5 sine of 0, and plus c. And this has to equal to 0, and since everything is 0, you get 0 equal to c, therefore your fx comma y, the final answer is this entire thing with c being 0. So let's write down the final answer. 3 over 2 x squared y plus 4 over 3 y cubed. The c being 0 was just a coincidence. Well, many times it does happen that way if you do that, but sometimes it's not. Okay, so don't think this is 0 always. Okay, so that's the final answer. Okay, that's the final answer.